In this lesson, we will examine the components that are used to convert hydraulic pressure into mechanical movement. Hydraulic actuators, or jacks, are used to convert fluid flow into linear or rotary motion. They vary in size and construction depending on the operating loads, but all consist of an outer cylinder within which slides a piston and seal assembly. Attached to the piston is a piston rod, or ram, which passes through a seal and wiper ring assembly fitted into the end of the cylinder. Three types of actuator are used for different purposes in an aircraft system. They are single-acting, double-acting unbalanced, and double-acting balanced. A single-acting actuator is one that is hydraulically operated in one direction only. The force to move it in the other direction is provided by a spring. This type of actuator is normally used as a locking device, the lock being engaged by spring pressure and released by hydraulic pressure. A typical application would be a landing gear-up lock. This type of actuator has more fluid in the cylinder when the ram is extended than when it is retracted. The surplus fluid is stored in the reservoir when it is not being used. Double-acting unbalanced actuators are the type most commonly found in aircraft systems. These are operated hydraulically in both directions. Because of the presence of the piston rod, the piston face to which the rod is attached has a smaller area on which the fluid can act than the other face. As we know, force is equal to pressure multiplied by area. So more force can be applied during extension of the piston rod than during retraction. If equal pressure is supplied to both sides of an actuator of this type, because of the difference between the areas on the two sides of the piston, the ram will extend. Normally, the operation which offers the greater resistance is carried out in the direction in which the piston rod extends. For example, in the case of landing gear, the rod will extend to raise the gear and retract to lower it. A double-acting balanced actuator is one in which equal force can be applied to both sides of the piston. This is achieved by having rods attached to both faces of the piston. It is often used in applications such as nose wheel steering and hydraulically powered flying control systems. Either one or both ends of the piston rod may be connected to a mechanism, or in many instances, the rod is connected to the airframe and the body moves to operate the service. When fluid is trapped between the piston of the actuator and a non-return valve, or a selector valve at its neutral position, a hydraulic lock is said to be formed. Because the fluid is incompressible and is unable to flow through the system, the piston cannot move, even if an external load is applied to it, and is therefore locked in its position. In our example, the gear lever has been selected to off. The weight of the gear is now being held by a hydraulic lock. Hydraulic motors are a form of rotary actuator, and are sometimes connected through gearing to operate screw jacks on such components as trailing edge flap drives. Illustrated here is the B747 trailing edge flap drive motor. It is mounted directly onto a gearbox, which in turn transmits the drive to the flaps through a torque tube. Hydraulic motors can also be used to drive generators or pumps. In some aircraft, they are used for driving a hydraulic pump unit, thus enabling power to be transferred from one hydraulic system to another, without transferring fluid. In the setup shown here, the hydraulic motor is driven from the yellow system, and the pump is pressurizing the green system. So this particular power transfer unit, PTU, would operate in the event of a main pump failure in the green system. Note that there is no exchange of fluid, so the two systems remain separate. The construction of a hydraulic motor is generally similar to the construction of a multi-piston pump, with the pressure which is being fed into the pistons being used to rotate them around the swash plate. However, the swash plate angle is usually fixed. Therefore, the speed of a hydraulic motor is usually dependent on the flow rate of oil into it. A hydraulic motor will often have a flow control valve in the supply line to it. The purpose of this valve is to maintain a constant flow of fluid to a particular component, allowing it to operate at a constant speed, such as would be required in a trailing edge flap system. A simplified flow control valve is shown here. It has a piston with a number of holes in it, through which fluid can freely flow. The piston controls the position of a variable orifice valve. Inlet pressure is felt on one side of the piston, with a spring pushing on the other. If the inlet pressure increases, then the flow rate through the valve will tend to increase. However, the increased pressure will be felt on the piston, which will move the valve towards closed, thus reducing the flow rate. The opposite will happen if the pressure reduces. The spring will push the piston to the right, the valve will open, allowing an increased flow. Thus, for variations in inlet pressure, the flow rate through the valve will remain constant. To summarize then, hydraulic actuators can be single-acting, double-acting balanced, or double-acting unbalanced. Irrespective of what type of actuator it is, if fluid is trapped between the actuator piston and a valve, the actuator will be hydraulically locked and unable to move. A hydraulic motor is generally similar in construction to a multi-piston pump. However, the swash plate angle is usually fixed. Consequently, the speed of a hydraulic motor is usually dependent on the flow rate of oil into it.